Hello, my name is Renee Lamb, and I'll be talking about the total synthesis of minus Mitrophorone A. So what exactly is minus Mitrophorone A? As you can see from the picture, it looks very complex, but where did it come from? What is it? So a little background on the compound. Minus Mitrophorone A was derived from the bark of Mitrophora glabra, or the Indonesian custard apple tree. The fruit of this tree is true to its name and supposedly tastes just like custard, and the fruit can weigh up to 1 kilogram. Not only does it taste incredible, but the minus Mitrophorone A found in the bark has shown cytostatic activity against various bacterial and fungal pathogens and cytotoxicity against selected cancer lines, such as MCF-7, which is attributed to breast cancer, H460 for lung cancer, SF-268 for various cancer types. In the bottom right picture, you can see that this is the fruit of the plant, and this is the bark where the minus Mitrophorone A was obtained. But for this synthesis, what makes it so special compared to past synthesis? So let's see how it was made. So looking at the retrosynthesis and going in the forward direction, we can get a breakdown of what occurred. As you can see, in the starting product, we have something similar to a malonate ester that has actually been alkylated with a methyl. Next, what occurred was another alkylation with an R group and also desymmetrization of the malonate ester. Desymmetrization of malonate esters is actually very complex and it has to do with the length of the R group. So the researchers actually found that the length they used for the R group in this reaction had the greatest yield for the desymmetrization of the malonate ester. So instead we got the carboxylic acid and an ester group. And then after they added methyl and an organoboron to the compound. Next, they reacted it with this cyclic compound with a good leaving group, and it underwent a Suzuki reaction. So in this part, the next reaction to form this alkene here was a major issue that they found. When doing this, they found that there is an EZ selectivity problem, which meant that since they're only trying to get minus Mitrophorone A, this product right here, there's an EZ selectivity problem. In order to get one compound instead of the other, they found it very difficult to reduce one of the alkenes from here and move it to the other one without getting a chiral compound. So for key reaction number 1, they problem solved it and formed a carbon-carbon bond with a stereoselective alkene, meaning that they only got one, the E or the Z product. And after that, they formed a nitrile oxide group right here. And for the next reaction, which is key reaction number 2, was that they formed 2 rings using the nitrile oxide group. And this was the formation of a fully substituted oxetane with specific stereochemistry. So as you can see, it forms a 6-member ring and a 5-member ring using the nitrile oxide. And then after they got rid of the 5-membered ring, and then they did another ring addition reaction to form the minus Mitrophorone A. So the key points of the synthesis were that compared to past synthesis routes, this one was highly antiselective and diastereoselective. This was due to solving the EZ selectivity problem using key reaction number 1. That means that they had a greater yield of their desired product and actually made the entire process a lot easier. This synthesis also uses a new reaction method to create the highly selective olefins, or this bond right here. Additionally, the complex ring was formed from a carbonyl oxidation reaction with a nitrile oxide group that underwent an intramolecular ring formation. So we'll be starting with the intermediate products between the malonate ester and this group right here. So some familiar reactions. So we are very aware of the oxidation of alcohol with DMP but we don't actually know the mechanism. So what occurs is that the electrons on the alcohol attack the iodide, kick off an ester, ester deprotonates the alcohol, and then the ester comes back to depronate hydrogen and form the carbonyl carbon and kicks off the DNP reagent, which also kicks off another ester to form the carbonyl. Next, from the carbonyl, we do the addition of a phosphonium ylide or the Wittig reaction, where phosphonium is attached by the double bond on the carbonyl, and then the double bond from the phosphonium and CH2 group attacks the carbonyl carbon. From that, we get a four-membered ring, and the carbonyl carbon oxygen bond removes and creates a double bond between the oxygen and phosphonium, and the phosphonium and CH2 group bond removes itself from the phosphonium and attaches to the CH2 and the carbonyl carbon to form a CCH2 bond. Now we're going to key reaction number 1, the highly selective tetrasubstituted alkene. So we'll be focusing on the Suzuki coupling reaction right here and the formation of this highly selective alkene. So as said earlier, it was very hard to create stereo-controlled tetrasubstituted dienes in organic synthesis. And previously they used Ireland-Clayton rearrangement, but after numerous attempts, they realized that they could not improve it anymore. They could not improve the yield of a stereoselective alkene. They realized they needed to do some research and found that only Shibasaki M had conducted research on synthesizing tetrasubstituted olefins using semi-hydrogenation of a 1,3-diene. Using his work, they refined the method by using cross-coupling and 1,4 semi-hydrogenation to get an enantioselective product. So what they did was they tested their methods with typical R groups and found it was very successful in creating just the E or the Z product in very high yields. Additionally, they then tried with protected alcohols, carbonyls, phenols, and even esters, and in each case, they're less than 5% of the undesired isomer, which means it was enantioselective. So part 1 is Suzuki cross-coupling, where they use palladium, PPH34, and aqueous sodium bicarbonate, which dissolves in water to form sodium hydroxide. And the product was a stereoselective diene. And in order to maintain this stereochemistry, they underwent semi-hydrogenation. After part 1, part 2 involves the semi-hydrogenation of one of the alkenes and the movement of the other alkenes to be in between R2 and R3. So part 2 involves using chromium and H2 to move one of the alkenes in between R2 and R3 while maintaining the same stereochemistry as seen in part 1. So for the first part of the Suzuki cross-coupling reaction, it undergoes oxidative addition with the active catalyst, where the active catalyst is now between the R group and the good leaving group, and the sodium hydroxide created from the sodium bicarbonate undergoes displacement, so sodium in the good leaving group comes out while the OH is attached to palladium now. And then it undergoes transmetallation so that the OH group is replaced with the group attached to the organoboron. And then after, we can see that we get this product right here with both R groups attached to palladium. And then it undergoes reductive elimination to create the carbon-carbon bond between the alkenes. And in part 2 of this reaction, we have the semi-reduction using hydrogenation. So what happens is chromium attacks one of the carbons on the alkenes, and the alkene moves between the R2 and R3 group, and then the other alkene attacks the chromium to form a 5-membered ring, and the chromium then attacks the H2 group, and then the hydrogen bond attacks the chromium so that both hydrogens are bonded to the chromium. Next, the hydrogen group shifts to the adjacent carbon, and the chromium carbon bond is kicked off to the chromium. Next, the last hydrogen shifts to the adjacent carbon, and the chromium is kicked off again. So So our product has the same stereochemistry as our starting material, but the alkene formed is in between the R2 and R3 groups. All right, so how does the rest of the molecule form? What is left? As we can see in the last reaction, we still have a carboxylic acid here, and that becomes a protected alcohol after a couple of steps, as we can see here, and that alcohol reacts with TBAF to deprotect it. So the fluorine on TBAF attacks the protecting group, which kicks off the bond between the protecting group and oxygen to make it negatively charged, and that oxygen then becomes protonated by water to form an alcohol. After we get this alcohol, it undergoes an oxidative reaction. So we get a carbonyl, and then it undergoes addition of primary amines to an aldehyde. So this NH2OH group attacks the carbonyl carbon, kicks off the double bond to the oxygen, then another amine comes in to deprotonate the nitrogen, and then that protonated amine then protonates the negatively charged oxygen twice, and then we get our good leaving group, which is water, and then the electrons on nitrogen form a double bond to kick off the water, and finally the amine deprotonates the positively charged nitrogen, so we have our resulting product. So now we get to key reaction number 2, which is the oxidation reaction of the carbonyl. So what occurs is that the nitrogen double bond attacks an iodide and the OAC group is kicked off. And also the alcohol group moves its electrons to form a double bond between nitrogen and oxygen. And after that occurs, the kicked off OAC group attacks the hydrogen right here and moves and creates a double bond between the nitrogen and carbon. And then another OAC group deprotonates the alcohol and places the electrons on the oxygen. After that occurs, the nitrogen forms a triple bond to kick off the I-phenyl OAC group. And here we get our nitrile oxide group. And what occurs is the formation of the 6 and 5 member ring, where this oxygen attacks the carbon from the alkene, and the alkene attacks the carbon triple bonded to the nitrogen group, and one of the bonds kicks off to nitrogen to form our final product. So what we have right now is this product, and after we have this product, it undergoes a couple more reactions to get to here, which is Me3OBF4, TMSOTF, ET3N, zinc, ACOH, H2, palladium/carbon. So the last steps of the products. So it reacts with the reagent here, potassium terbutoxide, O2, and PPH3 to form this product, where this OH group is now created. And after reacting with DNP SiO2, we get the OH group right here. This OH group right here creates a double bond. And then from this, it reacts with PHIOH OTS to form an ether group right here and a carbonyl. So this is our minus Mitrophorone A. So the pros of this synthesis is that this method was able to create more than 99% enantiomeric excess of minus Mitrophorone A. The methods developed for this reaction are useful to create highly enantioselective products. This is due to the key reaction number 1, where the cross-coupling reaction with the semi-hydrogenation of the 1,3-dienes formed a highly enantiomeric selective alkene. And this was actually a huge improvement from the past synthesis methods, just due to how much of the minus Mitrophorone A there were, because it was in more than 99% enantiomeric excess. Additionally, this synthesis method is very useful in research because that means that they're able to get more of the desired product, and they can conduct more analysis on its ability to fight against bacterial and fungal pathogens and the cantolines mentioned earlier, and also any other of its components that have not yet been discovered. Thank you for watching, and I hope you enjoyed.